Have you ever wondered how the electricity from a giant power plant can safely charge your tiny smartphone? The secret, my friends, is a truly remarkable device called a transformer. Science. A transformer is like a magical electrical translator. It doesn't create electricity, but it can change its voltage, which is like its electrical pressure, either up or down. Think of it as a gatekeeper for electrical energy, making sure the right amount of power gets to where it needs to go. Without transformers, our modern world of gadgets, lights, and appliances simply wouldn't be possible. They are the unsung heroes working silently behind the scenes, making our electrical grid work for us every single day. Let's consider some science in your daily life. That little block you plug into the wall to charge your phone. That's a transformer. It takes the high voltage from your wall outlet, which is way too powerful for your phone, and steps it down to a much lower, safer voltage. Your refrigerator, your television, and even the streetlights outside your window all rely on transformers. Big, powerful transformers sit on utility poles or in green metal boxes in your neighborhood, taking the super high voltage from power lines and reducing it so it's safe to use in your home. They are everywhere, performing the crucial task of voltage management. So, how does this amazing device work? It all comes down to a principle called electromagnetic induction. It sounds complicated, but the idea is pretty cool. A transformer has two coils of wire called windings, wrapped around a central iron core. When an alternating current, that's electricity that flows back and forth, goes through the first coil, it creates a changing magnetic field. This magnetic field then induces or creates a current in the second coil, without the two coils ever touching. It's like magic, but it's science. This transfer of energy through a magnetic field is the heart and soul of every transformer. Now, why do we need to change the voltage? It's all about efficiency. To send electricity over long distances from a power plant, we need to use very high voltage. This is because high voltage means lower current for the same amount of power, and lower current means less energy is lost as heat in the power lines. But you can't use that super high voltage in your house. It would fry your appliances. So we use transformers to step down the voltage to a lower, safer level before it enters our homes. The coil with more turns of wire will have the higher voltage, and the coil with fewer turns will have the lower voltage. It's that simple. Let's take a look inside this electrical marvel. The main parts of a transformer are quite simple: the core, the windings, and an enclosure or tank. The core is the magnetic heart of the transformer, usually made of thin, laminated sheets of soft iron or silicon steel. These laminations are insulated from each other to reduce energy losses. The windings are the copper coils that carry the electric current. The primary winding is where the electricity comes in, and the secondary winding is where the electricity goes out. In larger transformers, all these parts are housed in a protective tank, often filled with oil to help cool it down and provide insulation. The placement of these windings is very important for efficiency. Typically, the low-voltage winding is placed closer to the core, and the high-voltage winding is wrapped around the outside of the low-voltage winding. Why? This arrangement helps to minimize the amount of magnetic flux that leaks out and doesn't link with the other coil, which improves the transformer's performance. It also makes it easier to insulate the high-voltage winding from the core, which is usually grounded for safety. So the next time you see a transformer, you can imagine those two coils, nested together but not touching, doing their electrical dance. Sometimes, we need to make small adjustments to the output voltage. That's where tappings come in. Tappings are extra connection points, or taps, on the windings, usually on the high voltage side. By changing which tap is connected, we can change the number of turns in the coil, which in turn slightly changes the voltage ratio. This is incredibly useful for utility companies to fine-tune the voltage in the power grid, ensuring that the power delivered to your home stays stable, even if the load on the system changes throughout the day. It's like having a volume knob for voltage. The transformer core itself is the pathway for the magnetic field. Its job is to guide the magnetic flux from the primary winding to the secondary winding with as little loss as possible. There are two main types of cores, the core type and the shell type. In a core-type transformer, the windings surround the core like a sleeve on an arm. In a shell-type transformer, the core surrounds the windings, like a shell protecting its contents. The choice between them depends on the application, voltage, and power rating. Both designs are engineered to make the magnetic journey as easy and efficient as possible. Now for some math, but don't worry, it's awesome. The behavior of a transformer is beautifully described by the EMF equation. EMF stands for electromotive force, which is just a fancy name for voltage. The equation looks like this: E equals 4.44 times of times N times per mole. Let's break it down. E is the voltage in a winding. F is the frequency of the AC supply. In the US, that's 60 Hz. N is the number of turns in that winding's coil. And PEM is the maximum magnetic flux in the core. In simple terms, this equation tells us that the voltage is directly related to how many times the wire is coiled and how strong the magnetic field is. Science is cool. Transformers can be classified in many ways, depending on what you're looking at. Based on voltage, we have step-up transformers, which increase voltage, and step-down transformers, which decrease voltage. Based on their construction, we have core type and shell type, as we just discussed. They can also be classified by their purpose, like power transformers used in transmission grids, distribution transformers that bring power to your neighborhood, or instrument transformers used for measuring high voltages and currents safely. Each type is designed specifically for its job in the great electrical system. You can find transformers almost anywhere electricity is used. Giant power transformers are located at power generation stations to step up the voltage for long-distance travel. Then, at substations on the edge of towns, other transformers step it down. Smaller, pole-mounted or pad-mounted distribution transformers are found all over our neighborhoods, making the final voltage reduction before power enters our homes. And of course, tiny transformers are inside countless electronic devices, from your laptop charger to your microwave oven, each one ensuring the delicate circuits get just the right amount of voltage to operate correctly. So what makes a transformer good at its job? Performance is all about efficiency. An ideal transformer would transfer 100% of the energy from the primary to the secondary winding. But in the real world, there are always some energy losses. These losses come from two main sources: copper losses, which is heat generated by the current flowing through the resistance of the copper windings, and iron losses, or core losses, which are caused by the changing magnetic field in the core. A well-designed transformer minimizes these losses, making it highly efficient, often over 98 or 99%. How do we know how powerful a transformer is? We look at its rating. A transformer's rating is typically given in kVA, which stands for kilovolt amperes, or MVA, which means megavolt amperes. This tells you the total power it can handle, combining both voltage and current, without getting into the specifics of the load it's connected to. The rating plate on a transformer also lists other important information, like the primary and secondary voltages, the frequency it's designed for, and its cooling method. This information is crucial for engineers to use the transformer safely and correctly within the power system. Here's a very important safety tip. You can never ever connect a transformer to a DC supply, like a battery. Remember how transformers work. They rely on a changing magnetic field, which is created by an alternating current. DC flows in only one direction, so it creates a steady, unchanging magnetic field. This steady field can't induce a current in the secondary coil. Even worse, the primary winding has very low resistance, so connecting it to DC would cause a huge amount of current to flow, quickly overheating the coil and destroying the transformer, possibly causing a fire. So remember, transformers are for AC only. To make sure a transformer is working properly and to understand its characteristics, engineers perform two key tests: the open circuit test and the short circuit test. The open circuit test helps determine the iron losses. It's done by applying the rated voltage to one winding while leaving the other winding completely disconnected or open. Since there's no load, the current is very small, and the power measured is almost entirely due to the losses in the core. It's like checking how much energy the transformer uses just by being turned on. The short circuit test, on the other hand, helps us find the copper losses. For this test, the secondary winding is intentionally short-circuited, connected with a thick wire, and a very low voltage is applied to the primary winding until the full, rated current flows through it. Because the voltage is so low, the iron losses are tiny and can be ignored. The power measured in this test is almost entirely the heat loss from the copper windings when they are carrying their maximum current. These two tests give engineers all the data they need to know how efficient the transformer will be in the real world. So there you have it. From the power plant to your pocket, transformers are the silent, steady workers that make our electrical world go round. They are a brilliant application of the fundamental principles of electricity and magnetism. Thank you for exploring the world of transformers with me.